Welcome to the module. So, in this module we are going to see working of a DC motor, that means the controlling of a DC motor using data acquisition device. In the last module we have seen design of different signal conditioning circuits as well as a driver circuit that is required for the motor to drive it using operational amplifiers. At the same time we have also designed different controllers, PI controllers. We have seen interfacing the PI controller to the DC motor in order to drive the DC motor to a required set point. And we have also observed that depends upon what type of a controller that we are using it, and we have also seen that depends upon the gain that we have set to the controller, the offset voltages, the offset error, and the time it is taking to reach the set point will always changes. Also we understood that the working of a closed loop control system and the design of converting the encoder pulses output, which are digital, into analog output way, which linearly varies and maps with respect to the system input. But in the previous thing we have considered the DC motor RPM as frequency divided by 14, but we do not know whether it is going to give 14 pulses per one revolution or 7 pulses per revolution. So, in this module what I am going to show you is replacing a complete analog controllers which we were designed using operational amplifiers with a data acquisition module. So, we have seen different data acquisition modules, their working, the difference between the other data acquisition modules and everything. In this case I am going to use USB DAC, NI USB DAC. I will be interfacing DC motor using NI USB DAC. Of course, as any microcontroller as well as data acquisition devices cannot support the required current for the DC motor to drive it, as we have already designed a signal conditioning circuit or a driver circuit for the DC motor to drive based upon the signals received from the microcontroller as well as an operational amplifier, we will be using the same driver circuit interfacing the motor to the driver circuit, but the input to the driver circuit will be from data acquisition device. But how the data acquisition device will provide a signal to that, because since the data acquisition device will be interfaced to our PC, the PC, the algorithm which is running in the PC, which is being developed by using National Instruments Software LabVIEW. So, we are going to design the same controller, but the controller will not be on board, it will be on software. So, that is why this is called software in loop simulation. So, in a complete closed loop system, if you look into the screen, in a complete closed loop system, the system input will be set from the PC, error detector will also be set from the PC, and the controller is also designed and developed in a LabVIEW software which is also in PC, but this interface will not be a direct right now. This will be connected through a USB DAC. Whatever the signals based upon the controller and based upon the gains that we are digitally providing, that will be converted into an analog output by using data acquisition device, that will be given as an input to the driver of a DC motor, where DC motor is connected to the driver circuit. Then as we already seen, the motor is already integrated or interfaced with the encoder which gives an digital pulses, and since we are using a data acquisition device which can also support a counting pulses as well as which can also support a digital pulses, as well as it can also acquire analog input pulses by looking into by acquiring the signal either in a digital way or counter way as well as by analog signal way. If we can understand how many revolutions, or if we can understand the rate at which the RPM of the motor is rotating, such that by writing a code or by writing an algorithm in an LabVIEW software to make ourselves understand about how much RPM it is the motor is rotating, then giving it as an input to the negative at this point. By providing the output at this point, we can easily realize the complete closed loop system by integrating a DC motor externally and controller which is sitting in a software side, and we can understand the complete working of understand the importance of an operational amplifier, understand the importance of controller. We can also understand the working of DC speed motor control in order to maintain the RPM of a DC motor by using data acquisition devices as well as by using a software. So, here if you observe carefully, this is our USB DAC. This USB DAC NI6008, it is interfaced to a PC using our USB cable, and if you see the connections to this DC motor, this is our DC motor which is connected to an encoder. So, this particular part, the board, we have designed our driver circuit, and this is where we are interfacing the motor to the driver circuit, right. Here we can see, whereas when you look into that, we know that how many number of analog as well as a digital pins that USB DAC has. So, what we have done right now is we have connected the clock terminal pin to the encoder is powered by using USB DAC. So, here you can see these are the powering connections to our encoder plus VCC and ground, whereas the input to the driver circuit has been given from the 14th terminal of USB DAC, which means that it is an analog output. Now, what we are going to do is, in order to understand how many number of pulses this DC motor is going to provide or give per minute, we will write a program in NLabVIEW and we will acquire the signal, we will count the signal only for particular time duration, let us say 1 minute or 2 minutes. So, that based upon how many number of pulses per minute we are getting gives us the measure of RPM, right. So, for that case we have to understand which is our counter. So, if I look into the data sheet of ESP 6008, so here if you observe, we can see here that PFI, the 29th terminal, so it is our counter pin. So, let me connect the clock pulses, the output of clock pulses. In this case C1 I am considering it, either you can go with the C1 or C2 I am taking it. So, I am giving it to a counter input. So, to understand whether it is counting or not, what I will do is that I will create a test pins. So, I will open test panels. Since everything is powered using USB DAC, I can provide analog output of 1 volt. So, let me update. Then I will go to a counter input. So, here we can see PF0 start. So, one thing it is clear that depends upon the RPM, depends upon the input voltage provided to the driver circuit, we can understand the motor is rotating, but this is not clear to us to understand about how many number of pulses it is coming. So, what I will be doing is that I will write a code and I will be providing voltage from software. So, that depends upon the voltage, we will see in 1 minute how many number of pulses the motor is rotating. So, for that let me open LabVIEW. So, since our intention was to record, so what I will be doing is that I will be creating an express VI to acquire the counter signals. So, I am going to input data assistant device and I have to acquire counting input, then that should be edge count. So, since it is USB 600, it can support one counter signals, it has a one port of counting signal. So, here we can see whether we need a falling edge or rising edge. Then to understand whether it is working or not, here we can see it's keep on increasing, but until unless we stop and run the program, the counter cannot acquire reset the previous measured value. So, what I will be doing is that I am pressing OK, but idea was to understand what is the time it is taking or to understand about how many number of pulses it is going to generate per second. So, that means the system should automatically stop when the input time is greater than or equal to 1 minute. So, because RPM, rotations revolutions per minute. So, I will remove the stop button, instead of that I will go with elapsed time. I will set this elapsed time to 1 second. So, here we can see we can also set a target time from front panel. So, what I will be doing is that I will go to the front panel, I will create a control. So, from this we can create what is our target time. So, this is in seconds. So, if I mention 1, which means that it has to run for a second. Then since it is an elapsed timer, if you look into the help window, it says that indicates the amount of time that has elapsed since the specified start time. So, once you start the system, so once it reaches to the time, then it automatically provides a signal saying that if the time has exceeded based upon the if the time exceeds based upon the time that you have set it, then automatically it triggers the output as high in time has elapsed terminal. So, what I will be doing is that this particular terminal I will be connecting it to this. So, what happens? So, when this particular when the time has been elapsed, automatically this block provides a true signal to the counter. Then automatically data acquisition system will stop and it will stop the complete loop. And in order to accurately visualize, so we can also set how much time it has been taken elapsed before the stop of execution. So, what I will be doing is that I will create an indicator at this point. And in order to see how many number of pulses it has been counted, so I will set indicator, numeric indicator. So, it gives us the data of pulses. This gives pulses, but this is not our actual RPM. So, if I want to find out an RPM, we have to do a calculation. So, the thing is that these are the number of pulses we are getting with respect to this particular time, but RPM gives us how many rotations per minute. So, we have to measure with respect to 60 seconds, but whatever the pulses we are getting only for this particular time, elapsed time. So, what I will be doing is that I will take a multiplier, I will multiply this with 60. So, 60 indicates seconds, right. So, our idea was that for x seconds, for x seconds we are getting these many pulses, whereas for 60 seconds how many pulses it will be equivalent to. So, 60 into the number of pulses we got divided by elapsed time. So, I will take a division operation, I will go to numeric, divide, connect from here to here. So, whatever we will get will be RPM. So, I will take another digital output block and I will make it as RPM. I will take another indicator. So, I will make it as RPM. Irrespective of how many number of seconds it is rotating, so it gives us RPM. But right now if you observe, this can only acquire the signal, but if I want to even control the input voltage, so what we can also see is that we can take another data acquisition device in order to control the input signal provided to the driver. So, I will take another express VI, I will go to input or output, I have to make it as an output, I am taking it as an output, data assist. Or for our simplicity we can also use a simple measurement IO. So, what I will be doing is that I will create a new VI, I will call that VI into that. This VI is meant for acquiring the signal. So, for that I will take low level VIs. So, I will go to NIDAQMX in measurement IO. In this case I can create a channel, I will create a channel, but this channel is meant to provide analog output of voltage, but to which channel? So, we have to provide a control which indicates the specific channel, whatever the voltage that we set has to be given to this particular channel. So, this one I will name it as J1 A00. So, A00 indicates A0O, sorry AO0 indicates analog output 0 channel. So, let me zoom it, increase the font size. Then what I will be doing is that I will take another low level VI, this is for writing it. So, this is for one channel one sample, I will say data. So, I will take control, I will take a numeric control and connect it here. This numeric control is input to driver, input voltage to driver circuit. That means, which means that for DC motor, this I will be connecting it as input side, data, and this task should be connected here. Error to error, error in error control, then error output. So, in order to call this as a sub VI, in order to work as a sub VI and to be called from the another VI, we also have to set the terminals. So, what I will be doing is that I will take each connection, each pin, and I will be connecting it to this. Here we can see. So, depends upon the data type, it will automatically changes that particular pin to that default color. So, now I can also have an option, I also have an option to edit the icon. So, what I will be doing is that I will go to a template. First, let me delete this, then go to a template, our basic template. So, in this I will be writing DC motor, DC control, DC RPM control, whereas this one is A out. So, let me create a folder, DC speed control. So, the name of this folder I am saying it as this file as analog underscore out for DC motor. So, I will be calling that Vi here, and the input to this Vi control. So, let me keep it outside, so that at a time it can only pass a single data. Sorry, the physical channel I can keep it inside, but even outside is also fine, whereas the data that has to be passed to the system should also be before the start of execution. So, now let me set the physical channel to A00 and the input voltage to the driver say 1 volt. So, the time target is 1 second, and here we can understand what is the elapsed time as well as how many number of pulses it is giving, everything we can see here. Okay. So, let me run. So, initially this is channel where we are providing the analog output voltage, and whereas the channel for data assistant we have already done that. So, now what we will be doing is that I will be running the DC motor with 1 volt, and we will see what is an RPM and how many number of pulses it is doing it. So, when I run the program, okay, stop. So, the maximum value requested value is 10, the maximum value is 5 and minimum value, okay, stop. So, when you look into our USB DAC, we know that the USB DAC can only provide an analog output voltage of 0 to 5 volts. So, but whereas the default max value is of 10 volts. So, we have to replace the default with the 5 volt and the minimum value is of 0, create constant, so 0. So, now let me run, right. So, here we can see, so when the input voltage to the driver is of 1, the number of pulses we got is 212 and the RPM of the motor is 12,672, but with this we cannot understand. Let me change to input voltage to 2. Three, 4, 4 and 5. Yeah, makes sense. Now so we can see that repeatedly, even if we keep on running it, it is giving somewhere around 212, 213 pulses. So which means that we can understand that 212 is a number of pulses it is going to provide when the input voltage given to the motor is of 1 volt, but it cannot gives us how many number of pulses it is been generating it. For that we have to understand, we have to create a timer. Anyway, we already have a timer here, and for 1 minute 1 second we have to see how many number of times the motor is rotating it. So let us count how many number of revolutions it is making it. If you look into our, we are saying it is an RPM, this is an RPM of an encoder, but if you see that we have a total of a gear reduction ratio of 100. So what we also have to do is that the output of this has to be divided by 100. So this gives us RPM of a motor, irrespective of how many number of time that we are measuring it, the RPM of a motor is 117.37. So let me run once again. So this is the actual RPM, but we do not know whether this is an RPM or not. The reason is that we have to divide the RPM with how many number of pulses that the encoder is rotating. So in order to understand, we should know for 10 seconds how many number of pulses the motor is rotating. At the same time, we also count whether it has been rotated for 10 seconds or not. So let me do it. So what I will be doing is that I will be counting manually. So we will start 1, 2, 3. So it is taking only 3 complete revolutions. So that means for 10 seconds it is of 3 complete revolutions. So that means for 60 seconds it is approximately of 18 RPM. So we can see that here we can see for 10 seconds we have manually counted 3 number of full revolutions, which means that for 60 seconds, which is 1 minute, it is of 3 into 60 divided by 10, so which is nothing but 18 pulses. So but we are getting somewhere around 117.5. So that means 18 pulses corresponds to 117.5 RPM. So if I divide 117.5 divided by 18, 117.5 divided by 18, divided by 18. So we have to use 7 as it is not a 14, the 14 is the complete number of clock pulses we get from both C1 and C2, whereas 7 is from the single each channel. So which means that in order to actually find out the RPM of our DC motor, the output at this point has to be again divided with 7. So which means that for one complete revolution of a DC motor, we are getting 7 pulses from the encoder. So I will divide this with 7 to get an actual RPM. So, since these calculations everything should be it is easy to keep it outside. So, what I will be doing is that I am keeping it everything outside. So, let me run once again for 10 seconds. Right. So, 16 point. So, one thing it is clear that, so keep it 1 second, let me run. So, here we can see 16.2. So, that means for 1 voltage the RPM of a motor is 16.6. So, for let me change to input voltage 2. So, here we can see the RPM is 42, for 3 69, somewhere around 70, for 4 97. So, for 4 it is 96.6, 97. If I change it to 5, (124), 125. So, again for 1 we got for 1 volt we got somewhere around 16 RPM. Let me change to 2 volt, we got 43, let me rerun second time. So, 43, 44, whereas for 3 so we are getting somewhere around 72, whereas for 4 volt (99), and for 5 volt it is somewhere around 125, 126. Now, if I plot a graph between these two, yes, this is completely it is linear, and we can see, we can also plot a trend line and we can see its value too. So, that means the slope of the line is 27.3 and the offset is 10.7. So, that is clear, which is also equal to what we have done in our the previous consideration, but only thing is that there we have considered 14, but actually speaking it is only 7 pulses per revolution. Okay. So, now we understood how to do the calculation and everything, but what we have to do, our intention was to design a controller in LabVIEW, interface the motor using data acquisition, which we have already done, but we have to understand with respect to different controllers and with respect to the gain parameters of the controllers, how exactly the motor is going to control it.